Okay, so we're continuing our discussion of lines in 2 and 3D, and so we finished here with an example of writing the equation of a line in parametric vector form. And so again, just to remind us, for a line in any dimension, a line is defined by a point, let's say point P, and direction Q, and so then we can write the line as P plus T times Q. Okay, and so just as an example, if we want, how about if we have the point 1, 2 plus T times, let's just say 2, 1. Let's see if we can write this in terms of, let's see if we can write as y equals, let's say y minus y0 equals m times x minus x0, because this is more in the point slope form here, right? Okay, well, we see the point that the line goes through is going to be 1, 2, and if the direction is 2, 1, right, that means that for every 2 over, I go 1 up, and so therefore the slope is going to be 1/2. Okay, and so now I have my point and my slope, so the equation of the line is just going to be y minus 2 equals 1/2 times x minus 1. Good. Okay, so how about if we get a little trickier? Suppose that I have something, oops, I changed my box there. Let me get this over here. Okay, so what happens if I say, what is, I'll just go ahead and start at 1, 2, but what happens if I change that function in the front? How about if I say e to the t times 2, 1? What is that going to look like? As t runs from minus infinity to infinity. Well, geometrically, we're still thinking of starting at time, let's see, I guess here, well, this is a good question. If I'm at this point 1, 2, and then my direction is in the direction of 2, 1, so that's a slope of 1/2 there, right? So what this is really, this is the full line through this point. However, does this expression give us the full line as t ranges? Well, for one thing, if t goes to minus infinity, what's happening in this expression? Well, as t goes to minus infinity, that means your exponential term is approaching 0. So maybe I'll write it over here. E to the t approaches 0 as t goes to minus infinity, but e to the t is never equal to 0, right? And so therefore this half of the line we can erase, and so as t goes to minus infinity, we're approaching the point 1, 2. Okay, so this is t going to minus infinity, and so then what happens as t goes to plus infinity is we just go off to infinity in this direction. So this is where we're going for as t goes to plus infinity. Good. All right. And so let's see, where are we at t equals 0? At t equals 0, we're at the point 1 plus 2 is 3. 2 plus 1 is 3. We're at the point 3, so maybe this is the point 3. Close enough to scale. Good. Good, so that's the point 3. Very good, so that's what that looks like. And so notice that this is more like a ray. This is a ray rather than the entire line, because we actually stop here at the point 1, 2. Good. All right, so let's go ahead and continue on here to page 5 of our notes now. because we haven't talked about differential equations yet. We've been talking about lines. So we're going to be looking at differential equations of the form x prime equals ax1 plus bx2. That's x1 prime. x2 prime is equal to cx1 plus dx2. And so notice that that could be written as x1, x2 prime equals a, b, c, d, x1, x2. Or you could write it as vector x prime equals matrix A times vector x. Good. So this notation is all equivalent to each other. Okay. So what's the solution to this? The solution to the system is a function x of t, right, which is x1 of t, x2 of t, that satisfies the matrix equation. Okay, so maybe we can take a look at one. Okay, so let's try an example here. Let's try to show that x of t equals e to the minus 2t times minus 1, 2 solves the system x prime equals 0, 1, 2, minus 1 times x. Or you could say x1 prime is equal to x2, x2 prime equals 2x1 minus x2. Okay, so how are we going to show that? Well, this is our x1 and our x2. So let's write that down here. x1 is equal to minus e to the minus 2t. Therefore, what is x1 prime? Well, x1 prime will be 2 e to the minus 2t. x2 is equal to 2 e to the 2 minus 2t. So therefore, x2 prime is minus 4 e to the minus 2t. And so these together, if I factor out the e to the minus 2t, will leave me with a 2 minus 4. Okay. Now, I want to see if these two functions satisfy this relationship. So if I take x1 prime, that we already computed. Let me do it a different way. Let's go ahead and just compute this side. x2 is our top. x2 is equal to 2 e to the minus 2t. That checks. And then what do we have? 2x1 minus x2 is equal to 2 times minus e to the minus 2t minus 2 e to the minus 2t, and that is equal to minus 4 e to the minus 2t. And so we see that these two equations form e to the minus 2t times 2 minus 4, and you will notice that these two expressions are exactly the same. I don't know how that changed to a red. Okay, that was e to the minus 2t up here. Good. Alright, so that's how we verify that a solution works for a system. Let's see, there's some other problems here on I'm looking at examples 1 and 2 on the worksheet. It's getting to be a 9-minute mark, so I'm going to stop here and we'll take a look at the system of tanks in the next example.